Yeah, it's a great pleasure to introduce Sinead Williamson today. So she's from the University of Texas at Austin, and she's worked quite extensively in Bayesian non-parametrics, both in terms of computation, in terms of scalable methods, mostly, and also in terms of network models. So I'll hand over to Sinead.
Thank you, and thanks for inviting me here. It is a great consolation for not having seen everyone in Chile last week. So as Jim said, if you know any of my work, I do a lot of stuff on scalable Bayesian non-parametrics, particularly parallel MCMC for Bayesian non-parametrics. What I'm going to talk about today has some similarities with that. It's scalable inference and it involves Bayesian non-parametrics, but it's more scalable inference with Bayesian non-parametrics rather than for Bayesian non-parametrics. So we're going to be using ideas from Bayesian non-parametrics in order to do something like Bayesian inference in normalizing flows. And I'm sure there are many people with much more knowledge of normalizing flows than I have, but I'm sure there are also some people who could do with a refresher. So I'm going to start with introducing the general idea of normalizing flows. Wait. Okay, there we go. So the basic problem, standard one in statistics, is we have samples from some distribution. So this running example is a little 1D histogram of samples, and I want to know the PDF of that distribution. So typically what I'm going to do is say, I'm going to assume some parametric form for that PDF. Okay, so I'll specify a family of distributions. I'm going to be working entirely in continuous distributions with PDFs here. And I'm going to learn the parameter phi or phi hat within that family of parameters that best fits the data. And typically by best fit the data, I might be thinking in a maximum likelihood setting. So I'm going to find the parameter that maximizes the log likelihood of my observed data points. So the only thing left to do, apart from figuring out how to find that max likelihood, is to specify this family of distributions. And today, what we're going to do is use a change of variables approach to specify our family of distributions. So I'm going to start off with a latent distribution H, which is going to be a simple, easily understood distribution with no free parameters. And then I'm going to come up with a family of invertible mappings, G, which are parameterized by some set of parameters phi. Okay. And from this, I can characterize a probability distribution by saying my data is distributed according to h of z pushed through this function g sub phi. Okay. And if I've picked g sub phi to be invertible and differentiable, then I can calculate the PDF of the resulting distribution by looking at the PDF of the pre-image of my data under that latent distribution and scaling by the derivative of the inverse mapping, right? Or if in a more realistic setting, I've got multivariate data, that would be the determinant of the Jacobian there. Okay, so again, in nice simple examples, I might have that latent distribution H be a normal, no free parameters here, that's known, I know it's PDF, and my mapping be phi to the z, right? So this is kind of a generalization of a log normal distribution. I can then easily get the PDF of X for any given value of phi. And because in this case, I have a function that's differentiable, I can then use maximum likelihood, I can then use gradient descent on phi to get the maximum likelihood parameter of phi for my data X. Okay. I know you all know what gradient descent looks like, but I took the time to make some pictures, so I'm going to show you some pictures. So we'd start off with some value of phi, and then we take the derivative of this, or the log of this likelihood probably, and do gradient descent until we eventually converge to a local minima, and then say that's our best fitting distribution. Okay. So far, so familiar. We all learned this in an undergraduate statistics class, probably. It's an old idea. What normalizing flows do is take this old idea of change of variables and modernize it by parameterizing that change of variables using a neural network. So instead of being something like phi to the z, that function is now going to be a neural network. Now, it can't just be any neural network because we need it to be invertible, right? And an MLP, say, is not going to be invertible. So this is what sets it apart from something like a GAN, where we have a mapping from a latent distribution to observations, but it's a one-way mapping. We can't get back to the latent distribution. Now, while a standard neural network isn't going to be invertible, we can easily, with a little bit of thought, we can construct neural networks that are invertible. Right, so here's a basic way we can do this from this paper by Laurent Din, which is one of the first uses of neural networks in this context. Right, so they have some latent distribution, say a Gaussian, on a d-dimensional space. And what we're going to do is take that d-dimensional input and divide it into two chunks. Okay. And for the first chunk, we're just going to use an identity mapping, right? So the first little d elements are just going to be mapped to themselves. And then the second chunk are going to have a more sophisticated transformation that uses those first little d elements as kind of a key. So they're going to be mapped to themselves plus some function of the first little d elements. Right? So here, this f sub phi now can be any function. It can be an arbitrary non-invertible neural network, but the way that we've constructed this with this sort of key structure means that the entirety is going to be invertible. Right? So the first half, obviously trivially invertible. And then once we know the first Z1 to D, we can use that to unlock the second part, right? This is kind of a simple example of how we can do an invertible neural network. Since 2014, there's a whole bunch of more sophisticated examples. But this is sort of a proof of concept to show that you can do it. Okay? In this case, we can compute that determinant of the Jacobian very easily. That's something we want. In this case, it's just 1, which is nice. And we can also use this as a building block, right? So just like in deep learning, we stack layers of neural networks to get very flexible functions. We can stack these G sub phis to get more complex change of variables. Right, so I can apply one transformation and then run that through another transformation, etc. And then I can unpeel those layers when I'm inverting it. Right, so once I've got one invertible neural network, I can just keep stacking them. And that's nice, partially because you can get more complicated things, but also because you can avoid having the first D elements be the same. Right, so I could alternate which of my elements are going to be the key here. So perhaps in the second row, the second half of the elements are going to be given the identity transformation, and the first half are going to have something more complex. Okay, so we can parameterize a change of variables using a normalizing flow. And this is something very powerful. It's become increasingly popular in machine learning, and you can get some very high quality estimates of really complicated distributions such as images. And because we picked something that was differentiable, we can calculate the maximum likelihood parameters just by doing standard gradient descent or your optimizer of choice. Okay? And unlike things like GANs, it doesn't need us doing anything with randomization. We don't need to do the reparameterization trick or anything. It's just turn the gear on gradient descent and boom, which is great. But I feel like with this audience, I can say maybe we might be missing something just doing gradient descent here. I feel I don't need to argue this strongly, but we're missing out on any sort of uncertainty quantification, right? We're picking a single PDF when actually it might be more appropriate to say we don't know what the actual true PDF is, but we can express our uncertainty about it. And again, with this audience, it might be reasonable to say, let's be Bayesian. Let's put a prior on the parameters phi that, remember, are the parameters of these neural networks that we use to construct this invertible change of variables. We'll take our observations and we'll somehow calculate the posterior distribution of phi given those observations. Now, you're going to be shocked to learn posterior inference in a neural network is not analytically tractable. This is going to be hard to do in practice. Right? We're going to need to do something like Hamiltonian Monte Carlo, which is going to take a long time, or use some sort of approximate inference technique, maybe variational inference, maybe something like Monte Carlo dropout, which is going to involve introducing a whole bunch of approximations and is also going to, probably take longer than just doing gradient descent. Now, that on its own is maybe not reason enough to abandon the Bayesian paradigm, right? I do Bayesian nonparametrics. I'm okay with my samplers taking a long time to run. But there's another kind of deeper issue with taking a Bayesian approach here. Particularly if you subscribe to a kind of subjectivist Bayesian viewpoint, that one of the advantages of being Bayesian is that we can start off with our prior beliefs and update those prior beliefs as we see more data. I don't know about you, but I don't have any prior beliefs about the parameters of a complex neural network, right? They're famously a black box. I don't know what they should be. I don't have any intuition of how their values, how their variance, how their correlation structure maps to the output, right? So I don't really have any way of eliciting prior knowledge about what this normalizing flow should look like. Even if I feel, yeah, it's probably going to be a PDF like a mixture of 3 Gaussians, I don't have a way of capturing that in my prior. And what people typically do is say, I'm going to use a independent Gaussian prior with some sort of variance for each of the weights, which is fine. It means we can do Bayesian inference, we can update the posterior, but we are losing something about that sort of why be Bayesian idea. So what we're going to do is come up with a way that kind of avoids these two problems. It's going to be more scalable, and it's going to have some of that Bayesian-ish property of having prior information. So in order to do so, let's step back a little and go back to our original goal. We have some data, x1 through n, and we want to learn about a set of parameters phi in a way that characterizes our uncertainty. And depending on my viewpoint, my training, my preferences, how I'm going to solve this problem is going to vary. So if I'm a Bayesian, as I was on the last slide, I might say, well, I'm going to put a prior on phi, and I'm going to find that posterior. Easily said, maybe not so easily done. If I'm a frequentist, I might say, I'm going to start with coming up with some estimator, phi hat for phi, maybe a maximum likelihood estimator. And then in some way, I'm going to explore the relationship between the true parameter phi and the estimate phi hat, and then maybe come up with, say, confidence intervals that I can use to express my uncertainty. And I hope the machine learning people on the call will take this in the tongue-in-cheek manner in which it's intended. If I'm a machine learning person, I'll start off with the frequentist approach and then stop when I come up with an estimator. So 3 different ways of doing things. And they all give different answers to the question of how do I characterize my uncertainty about phi. But as my data size increases, these answers get closer and closer, right? And that's why the machine learning approach is usually fairly reasonable. They have a lot of data. There probably isn't as much uncertainty as the data sets that statisticians work with. So while these approaches are different, as we get to having infinite amounts of data, everyone's answer becomes the same, right? So if my problem instead is I've got infinite amounts of data, or alternatively, assuming these are IID samples, I know my full data generating distribution F0, then everyone agrees. We don't have any uncertainty left. We know what phi is. We're just going to take the maximum likelihood version, right? So I'm going to take my true empirical distribution, or alternatively, all of my data, and I'm going to calculate the expected log likelihood with respect to that distribution and maximize that, and I'm done. There's no more uncertainty, problem solved. So that would be great, but we don't have infinite data. But thinking about it in this way, the problem of inference is that we're missing all of the rest of the data suggests a new way of thinking. Okay? This is a approach that several people have been working on lately. I totally failed to add Sonia to this list, but Sonia's been doing great stuff in this area. The first time I've seen it called non-parametric learning, which is the terminology that I'm going to use, is this Liddon et al. Paper. If at the end of this talk you're super interested in the topic, I highly suggest you go back to this upcoming Fong et al. Paper, which is going to be a JRSSB discussion paper, but now you can find it on archive. You'll like it. It's a great paper. I digress. So what this line of thinking does is say, well, the problem is we don't have all of the rest of the data. But if we did have that data, we'd be fine. So rather than putting a prior on phi, let's specify something that captures our uncertainty about all of the rest of the data. Or alternatively, about what that underlying empirical distribution function looks like, given the things we've seen so far. Right? And so I'm going to take the approach of thinking about the underlying distribution function F0. In that second Fong et al. Paper down there, they take the approach of thinking more generally in the concept of infinite sequences, which is another thing we can do here. So once we've specified a distribution on the latent, latent's the wrong word, on the true empirical function, we can then come up with this non-parametric posterior, which isn't necessarily going to coincide with the Bayesian posterior. I put this wiggly line on top to show that it's not the same posterior as we're used to, where we're going to take our object of interest, that if we had full data, we would know exactly. And we're going to take the expectation of that with respect to our distribution over what that underlying data generating mechanism actually is. So this is a Bayesian-ish approach, but it's kind of starting from a different viewpoint. And this different way of thinking about things is going to solve a lot of our problems when working with normalizing flows. So first off, one of our problems was we don't really know how to put a prior on the space of weights of a neural network. But here we've got something like a prior, some sort of distribution, this pi sub f, on the space of all of those observations we haven't seen yet. Now, while I might not have a good idea of what the parameters of the neural network might look like, it's reasonable that I have an idea of what sort of distribution I'm going to look at. Right? So it's maybe more reasonable to expect a practitioner with knowledge of the data domain to specify a good distribution pi sub f. So kind of an example of this is we could use the Posterior of a Dirichlet process. So I can specify a Dirichlet process with some base measure h, where that base measure is something that contains our prior intuitions about what the data is going to look like. Right? So this could be an empirical distribution from a related data set. It could be the outcome of a different probabilistic model that's been trained on the data. It could be something that's handcrafted by experts based on their domain knowledge. Right? Whatever the case is, it's something that depends on things we can see rather than the parameters of a neural network. And then we're going to say our distribution pi sub f is the posterior given the data and that underlying base measure, right? Which feels very intuitive. We're saying our best guess of what the full data generating process is like is going to have atoms at the locations we've seen. Makes sense, we know those data points are in there. But it's also going to contain that sort of prior base distribution, right? So it's sort of a randomized convex combination of what we thought initially and what we've seen. So the Dirichlet process is what Fong et al. Used in this paper. I'm using it because it's easy. You could easily sub something else in here, but Dirichlet processes are easy to work with. I'll just note as an aside, if we take the degenerate case of this, where alpha is 0, and we have basically a finite Dirichlet process / Dirichlet distribution here, then that gives us back the Bayesian bootstrap, right, that you might be more familiar with. So that's a nice thing. Our prior, or I keep putting prior in inverted commas, it's not really a prior, but our injection of uncertainty is on something that we know something about. Another benefit, if you're interested in sort of generalized Bayesian approach, is that we don't actually have to have the log likelihood here, right? We could think about finding the limiting minimizer, I should have changed that to min, not max, I didn't, of any loss function, which we can use to get at some other functional of the data, right? So for example, if I wanted the median of the underlying distribution, then I could use a loss that is the absolute value between x and phi. Right? We're not going to make a huge amount of use of that right now, but it's a thing that we can do. And then finally, the other thing that is going to be nice is that we can come up with a trivially parallelizable Monte Carlo sampler for sampling from this. So here's what that looks like in the very general case, right? This isn't just for normalizing flows. This also isn't something I've come up with. So we have some set of observations. What we're going to do is we're going to generate B samples that I'm going to call bootstrap samples with analogy to the Bayesian bootstrap from that non-parametric posterior. And we can do that by first sampling from that pi sub f, that distribution over the data generating mechanism. Here I've assumed that that's an atomic non-parametric measure. I'm going to be using the Dirichlet process. You might be thinking, Sinead, you said that this was easy. Here you've got an infinite dimensional object. I'm not actually going to do that. I'm going to sample from a finite approximation to that Dirichlet process posterior. So what I'm actually going to do is sample some number of pseudo observations from my base measure. I'm going to combine them with my actual observations, and I'm going to sample weights according to a Dirichlet. And as m goes to infinity, that's going to converge in a weak sense to the Dirichlet process. But we're going to pick a more manageable number of m. There's other things you can do here, other approximations, but this works pretty well. Then once we've got our sample, we're going to find the minimizer of this weighted loss, right? Where this is just summing over the loss per data point or pseudo observation multiplied by its weight. And this is going to be roughly the same cost as optimizing our original MLE. Right, so if the number of pseudo samples is small relative to the number of observations, then it's basically going to be the same computational cost. And all of these can be parallelized. So if I have an unbounded number of computers to do this on, then I don't need to take any more time than I would for a standard MLE estimate. I don't have an unbounded number of computers. I have 2 computers personally, which, you know, is plenty of computers for one person. We'll get onto that in a moment. But if I did, I could do this with normalizing flows, train hundreds of them, and then combine them to get a posterior sample. I can't do that, but I trained 5. I trained 5 samples, and that took quite a while because training a normalizing flow takes time, even on a really simple example. So here I've got an example of what this algorithm will give us out as a approximation to the non-parametric posterior using just 5 samples on some toy data. So at the top here, I've got samples from basically like a sawtooth plus Gaussian noise. Right? So the X is just Gaussian, and then the Y is Gaussian plus sawtooth. And this row here is the density estimate that we get out by training a standard normalizing flow. And this one is a masked autoregressive flow, doesn't really matter. You can see, because this is quite a small low dimensional case, by the time we've got up to 512 samples, we've got a pretty good estimate of the density. But when we're in a low data regime, we haven't got the world's best estimate, right? We're being very convinced that we've got high probability where we have observations and low probability elsewhere. And then we're also tending to have like fairly aggressive confidence in where this PDF goes outside of the data, right? So fine if we've got lots of data, overfitting to small data. As we go down here, I've got those non-parametric learned versions with first alpha equals 0, so that's like a Bayesian bootstrap based on the data, and then increasingly high alpha concentration parameter with a base measure that's just a spherical Gaussian, right, centered on the data. And we can see that as we even just go down to the Bayesian bootstrap version, we're getting more uncertainty. And as we start incorporating that prior-like base measure, we're getting more and more close to that sort of Gaussian prior knowledge. Okay. The other thing you'll notice is these don't look super like a Gaussian. They look kind of like a kid gone crazy with a sparkler. Right? That's because I've only done 5 samples here. If I had the compute and the patience to get like 100,000 samples, these would look a lot more smoothed out. But I can't, because like I said, I don't have the compute. So this is fine in principle, but it's not going to work for more complicated examples where I want large numbers of samples. Okay, maybe it will in Google, but I'm not Google. So we're going to come up with something that is going to be more scalable, but still has this sort of behavior. And the intuition to this is, even though we're learning these independent flows, they're not that dissimilar, right? At the end, they're trained on similar data, just different weights. Maybe we don't need to be entirely independent when training. So what we're going to do is share some of the parameters, which means we only need to train those parameters once, and then let the other parameters describe the difference between them. Yep. So what I'm going to do is I'm going to have a shared neural network, G sub phi, just as I would in a single normalizing flow. I'm sharing this because it takes time to train a neural network. And then I'm going to have per bootstrap sample base distributions that now are going to be parameterized rather than fixed, right? So they're going to have a local parameter mu. So now my PDF has two parameters, mu and phi. I'm going to learn one global shared phi for all of my samples, and then individual mu's. So you can think of this kind of the opposite of what I was doing before. So previously, I had the same base distribution for each one, but different flows. Now I'm going to have the same flow, but different base distributions. And I'm not going to go complicated with that base distribution. I'm just going to pick a Gaussian with an unknown mean. I'm going to do that because I can easily calculate the maximum likelihood mean by just taking the pre-image of my data and pseudodata and taking the weighted mean using those weights from the Dirichlet process. Okay. So I've lost some of the flexibility by enforcing that we're sharing a flow architecture and parameters, but because that is a very flexible family of functions, and because these base measures can be arbitrarily spread out if they need to be, we still have a lot of flexibility to learn good functions here. All right, so here's what that's going to look like algorithmically. So we're going to start off as if we were doing a naive implementation of non-parametric learning. We're going to start with our data, and we're going to decide on a distribution pi sub f and a number, an approximating level n. I'm then going to train my normalizing flow, which is parameterized by phi, by repeatedly sampling weighted data sets from pi sub f, getting the maximum likelihood base distribution for that specific sample, and then taking a step to optimize my normalizing flow. Right, and I'm going to keep doing this, but with a different sample each time. So this is basically the computational cost of optimizing my flow, except I'm sampling from this Dirichlet and my base measure here, and I'm taking a weighted mean, both of which are fairly small fry compared with the neural network part. Okay, and I'm going to do this for some amount of time, and then I'm going to freeze my neural network and fix that. And so because I've trained it on a whole bunch of samples from my data generating mechanism, this should be fairly general. It should be robust to different samples. It should work well across the support of that distribution. Then I'm going to use that frozen neural network to generate my bootstrap samples by generating samples from pi sub f and just calculating the maximum likelihood mean for those samples. Put them together, and I will get approximate non-parametric posterior samples from the normalizing flow. Okay, so here's what those on that toy data samples look like. Right, so same setup. Here's my data. There's exactly the same normalizing flow. Now we're a lot more smoothed out, right? Because this is based on, I think, 100 samples rather than 5. But we still got a similar shape to before, right? It's still capturing what I would hope to do if I had more samples here, that I'm getting better or wider uncertainty. And as I increase alpha, as I increase my belief in that Gaussian base measure, I'm getting closer and closer to a Gaussian, right? Whereas as I have more data, I get closer to the empirical distribution. So I would argue that this is a pretty good approximation, and it's going to take a lot less time unless you have those infinitely many computers at your resource. Oh, a chat question. I can't see. Oh, okay, never mind. Not a question. All right. Where was I? Okay, here's the corresponding standard deviation. Again, what you'd expect. No line here for the standard flow because that doesn't have any uncertainty. But as we go down, increasing the weight of that base measure, we get more uncertainty and we're looking more like that Gaussian prior. And you can put any prior that you like here. In the paper, we've also got an example where we're using a Gaussian process. You know, Gaussian process is a better prior or base measure for this, so it works better, but the intuition is kind of the same. Okay, so we didn't come up with this in order to model a sawtooth. We came up with this to model real data. So let's get on to some real data here. So what I'm going to look at is 5 data sets that are tabular data, mixture of categorical and continuous variables from the UCI repository that are picked because they seem to be the ones that people who do research in normalizing flows use. So they're used in this paper, several other papers, and I've used the version that's like all nicely pre-processed from those papers. So here's their number of features, various sizes, and the size of the test set that we're going to be evaluating on. They all have training sets that are, about 5 times, I think, bigger than this. We're not going to use the whole training set because if you have thousands and thousands of data points, there's probably not much uncertainty left, right? The reason you want uncertainty is because you've got relatively few data points compared with your parameters. So, you got higher uncertainty. So what we're going to do is take the first 500, first 1,000, first 5,000 from these data sets as imaginary small data sets. And then we're going to use a more recent, fancier normalizing flow called a neural spline flow as our base measure, as our base flow. And for our base measure, I know that the pre-processing made all of these have 0 mean unit standard deviation across each feature. So I just used a spherical Gaussian as the base measure. Okay. So let's take a look here. Here, what I've got for each data set is the test set log likelihood for the 500, 1,000, and 5,000 N data sets. Right? You'll be shocked to learn that the more data you have, the better you do. And so here we can see on the x-axis, the far left one is standard normalizing flow, no uncertainty. Then alpha equals 0 is that Bayesian bootstrap type version, where we don't actually use the base measure at all. And then alpha is 10 and 100 are putting increasing weight on this Gaussian prior. Okay. And so we see that as we get to alpha equals 10, alpha equals 100, then we're across the board doing better than the normalizing flow with no uncertainty. Right? The difference is more dramatic when we have small data sets, which isn't surprising. Right? We're much more likely to overfit if we only have 500 data points. One thing I will note, which was surprising / disappointing, other work on non-parametric learning has often found that you do pretty well with setting alpha equals 0, right? The Bayesian bootstrap version. In some cases, we see an improvement from that. In other cases, so this guy, this guy, this guy with the n equals 500, that actually does worse. We don't have a solid answer for this. We have hypotheses, and those hypotheses are kind of based on the fact that even with the different weights, it's still very possible to overfit here, right? The flows are good enough that even with different weights on different points, we're still going to get very high probability around the data points. We're still going to get that overfitting because it can, right? Because it's highly parameterized. And at the same time, we are potentially getting something a little less stable, right? Because we're training using these weighted data points. So that's not a reason, but it's maybe a reason why alpha equals naught does well in more tightly parameterized models, but doesn't, this is the wrong slide, doesn't seem to do as well here in all cases. But still, despite that, I think this is really promising that we are able to do better by doing something that's like kind of a Bayesian thing and incorporating some very vague prior information. Now, I wanted to compare with other Bayesian normalizing flows. Turns out there's not much work on Bayesian normalizing flows. There are a handful of like special case Bayesian normalizing flows, none of which match this sort of data. So the one comparison that we've got is actually this idea called Monte Carlo dropout, which is this very popular idea from Galangaramani that if we use dropout, not just during training, but also during test, then that's an approximation to variational inference under a specific variational approximation. Okay. In many cases, this works really nicely. In our case, we didn't find any real benefit of doing it. And one thing to note as a possible reason why is this doesn't really have any way of imbuing any sort of prior information, right? So it's adding some uncertainty, but not in a way that is pulling it towards a prior distribution. So this is just one of those lines before. The others look kind of similar, but I couldn't fit them all on one slide. Okay, so that's basically the gist of it. I think this is a kind of nice exploration into how we can combine these new ideas coming out of the statistics community with stuff that people in machine learning are doing, which brings its own challenges of scalability and the need to make approximations. Right? I focused on how we can approximate that parallel inference, but I think there's a lot more we can do with matching those data generating distributions with the task. Okay? For example, if we've got structured inputs or non-IID cases. And while I'm really pleased with this work, I do think there are ways it could be improved. Right? So if I look back to this slide, we do see some evidence that we're not getting quite as high uncertainty, especially in like this very small n case, as we would under an exact model. And that's kind of to be expected. We're inherently coupling some of the parameters across these samples, which isn't going to let them be as different as they could be. We did explore some approaches to adding diversity, right? We'd hoped using MC dropout would help here, but it turned out it didn't. But I think it'd be nice to see how we can do something approximate that still pushes them apart closer to the independent case. And we still do get overfitting, right? It's kind of a neural network problem when we have small data. It's easy to overfit. We have found that adding regularization does help here. Like the second set of experiments you saw were with regularization. It means we no longer have that log likelihood correspondence. It's in more the loss case, but it still has a valid interpretation as uncertainty of what a trained regularized neural network would look like. Unfortunately, because of the way that this is constructed, having this idea of a loss that's an expectation of a per datum loss over the data generating mechanism, we can't use some of the popular, or we can. Theoretically, we shouldn't use some of the popular machine learning tools like early stopping because they don't correspond to the sort of loss we're looking at. So I think that robustness is a really big issue with working with small data. I'm behind the ball. I had totally intended to get the paper on arXiv before today, and it is not there yet. It will be soon, I promise, or if you're impatient, then email me and I'll send you it. Or alternatively, read one of the many great papers on this area by Chris Holmes, Stephen Walker, Sonia Petrone, many others. And finally, this is all work with my PhD student, Evan Ott. He's about to graduate. He's great. So specific thanks to him.
Thanks, Sinead. That was very interesting.
Thank you.
Yeah, so any questions for Sinead? So I had one question. So you have these two versions, right? The version where you independently generate samples, and another where you have this kind of trick with this kind of algorithm. So have you tried both? Do you is the trick just really a trick to approximate the independent thing, or do you get more through kind of doing everything together in some way?
Yeah, that's a great question. So we've only tried it on the small data because I don't have the compute to do it on the big data sets, right? It takes a long time to train these things, and I don't have the compute resources to train them all exactly. But on the small data sets and on some, so we have, that's a lie. We have trained some small examples, but the examples are here. We haven't done a comparison. In many cases, especially on big complicated things, we found that actually doing the right thing does worse. And our hypothesis for why this is because then we're training a normalizing flow on one specific set of weights, which can mean we have like a very high weight on one data point and very low weights on the rest, which can give us a really unstable solution, which then gives very low log likelihood anywhere else. But because these have been trained using that kind of to be good for the whole distribution by using repeated samples, they don't have that sort of aggressive overfitting behavior that we've seen in practice when trying to do independent flows trained on a single Dirichlet weighted sample. So there is a certain amount of robustness that we seem to get as well, which is a benefit but wasn't by design.
Yeah, that's interesting. It's interesting. I mean, it seems like a natural thing to come out of doing it that way, maybe, because it kind of it's almost like you're regularizing things. You're kind of somehow constraining. So I don't really understand quite at the moment, but you're constraining something at least, and so you're kind of like in a smaller space somehow.
Yeah, it's. I agree. Yeah, it. And I think I'm stuttering. I'm not sure where I was going there, but yes, I agree.
Okay, I think Trevor's there with a question. Do you want to go, Trevor?
Yeah. So thanks for the really interesting talk. It's very fascinating work.
Thank you.
I was wondering, and maybe I just missed this at the beginning of your talk, did you try kind of the obvious thing, which is to just put a prior on phi itself and run some kind of reasonable MCMC scheme to see what you get out of it? I just wonder, is like the posterior so complicated that it's kind of pointless to try that, or?
The main reason that I didn't was so I probably should do. No, I haven't, mostly because I didn't have an existing implementation of that. So it'd be kind of doing it from scratch, and I just didn't, honestly.
I mean, I should say I totally buy your argument that specifying a prior on phi is kind of ridiculous, right? If you're thinking from sort of a proper Bayesian statistician standpoint, and putting a prior, as you've done, a sort of non-parametric prior on the data generating distribution makes a lot more sense.
Yeah.
But I do wonder, I mean, if you're looking at your log likelihood on the test data set plots, I wonder how well the sort of dumb thing would do there.
Yeah, and I especially here, like we're not using a particularly informative prior here.
Right.
There's a possibility it would do well. The MC dropout is arguably an approximation to that, which didn't help in this case. I think there are definitely, there's a whole literature on Bayesian neural networks where they show that they work well. People haven't really done that in normalizing flows, but that I don't think there's any principled reason for that, just people haven't got around to it yet.
Yeah.
So I guess it's not that I don't see any reason why using HMC on this wouldn't work. We just haven't yet.
Yeah. Would you mind if I asked one more quick one? Again, I might have missed this. Did you take sort of an empirical Bayes approach to setting the Bayes distribution in your Dirichlet process? So instead of having sort of a standard normal H, did you set it empirically from the data? And do you think that would help?
So on using a different flow, so Evan has some experiments which aren't currently in the archive, or the archive version that isn't. They're not currently in that, they're not fully complete, where he uses a empirical data set in order to do that. So kind of like sampling from that. It does seem, in his experiments, he gets better results with that empirical data set. So it's definitely
like the empirical set prior on the Dirichlet.
Yeah. So like using
using
a similar data set.
Cool. Thank you.
Yeah.
Are there any other questions for Sinead? Okay, so it seems like that's the question. So thanks, Sinead, for a very interesting talk.
Thank you.
And sorry about earlier with the mess up with the two Zooms.